Thanks a lot and welcome here. Alessandra already presented the project, so I'm not going to go so much into the project. I'm going to show quite a lot of fancy pictures, which were basically taken in the previous months. So first, well, this is Delfi-PQ. This is a 3P PocketQube, as Alessandra mentioned. And as you can see, we have a deployable antenna on the side, and you can see it in both configurations, deployed and undeployed. Well, this is how it looked last week. Now it's nicely in a box, and I'll show you instead what's inside. Well, this is actually the satellite seen from the inside. You see one of the side panels that has been removed, and you can have a look at the complete electronic system, all the electronic systems in there. We start from the top, and you can see what we call the antenna deployment board. Basically, this board is constraining the antennas to remain attached to spacecraft, and after deployment, there will be a burn wire that will release the antennas such that they can deploy in the final configuration. If we keep going down, you can see just below the antenna deployment board, you can see our power system, which is actually hooked up to the battery. The battery board, you see it hidden inside this nice box. This is a 3D printed casing, which is mechanically holding the battery cells to give us a little bit more rigidity for vibrations. These boards are directly connected to each other, and they're also kept very, very close, such that most of our, let's say, power section of the satellite is on this side. Well, the rest of the power section of the satellite, you don't see it so much, or you can see it somewhere here at the back and around the satellite, because all the solar panels have been, all the electronics for the solar panels has been placed on the solar panels themselves. So electronics fits on the inside, and the solar cells fit on the outside. At the beginning, our idea and our wish was to have a wireless satellite, basically no wires running around. In CubeSats, this is kind of a problem in the sense that when the satellite density increases, it gets more and more difficult to fit everything. So it's a little bit difficult to see, but if you look at this small section here and here, all the connections that we have in between our battery board and the solar panels are done using spring-loaded connectors. You can see them as well a little bit in this area, where the solar panels kind of press against the battery, and this system assures mechanical contact and also electrical contact. We went through a vibration test, and we also basically qualified the system, because one of our biggest fears was rattling or small movements of the spring-loaded connectors, causing basically degradation of the PCB. But that actually didn't happen during our tests. So we're very, very happy of the functionality of this system. If we keep going down, we have this gap from which you see some parts of the power electronics. Below, you can see our, well, okay, I'll skip that. You will see these two boards, this one and this one. They are connected with wires, basically because they have to go through this metal structure here. This is what we call BOB, or the breakout board, which is basically used to join two separate stacks, because we have the top and the bottom stack. If we keep going down before after the breakout board, you can see our onboard computer, and you can see here also our SD card used for storage. And if we continue all the way down, we see our communication system, which is directly mounted. This is the communication system having a dedicated board for our power amplifier and low noise amplifier that connects directly to our antenna facing board, which is all the way here at the bottom. As I said, we aimed at a satellite without wires. Well, we're almost there. We needed these to connect the breakout board, and we also ended up with an RF cable on this side of the satellite. And now we will see a little bit more about that. Well, if we look at the payloads, we have our attitude control system, which is having coils wound on a 3D printed spool. And we have three coils, one inside the other. What you see here is the Z-axis coil, which is the biggest, while the other two are inside. This is one of our payloads, and we will use it to give the possibility to students, as part of their education, to write an algorithm for attitude control. And as we are an aerospace engineering faculty, this is one of the courses students have to do in their curriculum. So what we will aim at doing once we're in orbit is have students write code to fit on the ADCS system and basically do in-flight software update, such that more groups will be allowed to test their algorithms. On top of that, we added a set of laser reflectors that you can see here in the middle. There's 4 of them, 1 per side, and they are mounted on this metal bracket. The main rationale for these laser reflectors is being able to know the position of the spacecraft with an extremely high precision. We are in the order of the centimeter from the ground. One of the rationales for going for the reflectors was that, well, a lot of people were scared that the orbit determination for PocketQubes would be much worse than for CubeSats, having basically a much bigger error. And with this, we want to prove this is not the case. So after launch, we have already had contacts with the International Laser Ranging Network, such that we can track the satellite and compare our position from laser measurements and from radar measurements. If you continue going down, we have another board here in between, just below our onboard computer, which we call secondary computer. That's almost the same system, and it's not used by default. But the goal is giving the possibility to students to write their own algorithms. Imagine, for example, analyzing the telemetry on board for some purpose. Well, that we can do on this board, which is basically listening to everything that is communicated on the satellite bus. There is no software right now, so basically it doesn't do much more than say, hey, I'm alive. But our goal is to give students the possibility to write software, and then we will upload it to the spacecraft later on. Last but not least, we have another payload. This comes from a collaboration with another Dutch group, and which aims at building a low-frequency radio telescope in space. And with this mission, we're demonstrating some of the first building blocks. What we have basically is a low-noise amplifier that is actually fitted here. That's the board where the cable comes from, which is supposed to receive extremely low frequencies. And we're talking between 500 kilohertz and 30 megahertz. Of course, we don't have a big antenna for such frequencies, so we only have to rely on those small 18 centimeters long rods. But actually, we're not looking right now at astronomic sources, we're looking at Earth noise. So our goal is characterizing the Earth noise and demonstrate that our low noise amplifier works. In order to do that, we also have a readout board here that will acquire measurements. So let's go. Now, what am I going to talk today? I'm going to talk a little bit more about our integration. But before we reach the integration, there's a lot of testing that has been done. In particular, we decided to start with automated testing for several reasons. One, and I think one that proved our concept was very valid, is the fact that the university entered the lockdown in March, basically forcing everybody to work from home, including students that were working on the project. In that sense, it was impossible to have people on campus to actually test the boards. So what we built was an interface board that you can see at the top, which is connected via USB to a computer. The computer runs an application that is exposing all the satellite bus directly on a web socket online. This basically meant that students could simply, from their home, write a simple script that would communicate over a WebSocket and that would directly communicate with the satellite bus and all the satellite subsystems. This allowed them to do a lot of testing that they would not have been able to do otherwise. What you can see at the bottom is that we also shared most of our software on GitHub, so you can have a look at the testing software we developed. Automated testing gave us a lot of other possibilities. In particular, we have dedicated test tools which generate automatically test reports. You can see an example here at the bottom, where all the different boards have a standard set of tests that are executed. We simply need to plug the board on our system and run the test script. This can be done from home or from the computer in the lab. And basically what we get after a few minutes is a complete test of all the functions. We created it in a hierarchical way such that we can share code between all the different systems, such that we can test, for example, the standard services that every board has. And quickly, as you can see here, within a minute, we can see which functionality of the system is working or not. This was actually key for satellite development because we found out that in the last weeks, we had still a lot of work to do because of delays in the project, and testing could not have been sacrificed there. So thanks to this system, within minutes, we could see if a board was running or not. We also developed more complex tools. You can see an example here of our power system testing tool, which basically allowed us to leave the power system together with some other boards running for days and days. And what we were simply doing was collecting the health of the battery, or for example, simulating power incoming from a power supply and seeing how the microcontroller would react. This allowed us for test durations of up to 10 days right now, which allowed our software to be rather robust the day we started the final integration of the satellite. Well, one example of what I just showed you, this is a test which we did by applying power from a lamp in the lab, and basically recording for a long time the behavior of the system. We had these tests, as I said, running for days, and that allowed us to build confidence on the system. By reusing most of the software on the different systems, we basically created a fairly robust architecture that we hope will prove itself in space shortly. Some other tests we performed, again, most of these things were done from home or at home, basically because most of our testing period happened during the lockdown. This is actually a test that was run at 𝗖𝗁𝗁 place. So you can see an engineering model of the satellite having actual cells, which has been put in front of a lamp. And this lamp was providing power, and at the same time, we used the telemetry that was acquired to validate our thermal models, basically brute forcing the thermal properties of the system, conduction between boards, radiation, and of course convection, as in this case we had no access to a vacuum chamber, to basically optimize the models. And as you can see, we managed to fine-tune quite a lot most of the properties, as most of the phases we can see clearly that simulation and measurements were very, very close. This allowed us to build quite a lot of confidence in the overall system, such that the testing phase in the end, in the last weeks before launch, could be much simpler. I talked about the antenna deployment board, and now you can see a close-up of this board. This system is holding the antennas. You can see the 4 antennas, 1, 2, 3, and 4, being held down. They're held in a recess on the PCB, and by holding them there, we also press a deployment switch. 4 burn wires are used on this board on the external side to retain the antennas. And we use these 4 resistors to basically burn the wire. Testing was complicated as the burn wires in the end, with this configuration, they require quite a good precision in length. This is something we couldn't really achieve ourselves by basically tying the knots ourselves. So these are commercial wires that have been bought from our partner 𝗖𝚻 in the Netherlands, well, located less than a kilometer away, which could provide us with these standard wires, which are fairly good in terms of repeatability, because the length of the different wires is fairly constant. And this we found out being one of the hardest part in the process. What you can see the length being fairly constant by the fact that all the springs are roughly the same length. Also meaning that the pressure or the force on each antenna and on each burn resistor is constant. Why is it important? Because this gives us very repeatable conditions for the deployment. And you can see here at the bottom a thermal picture taken during the deployment of one of the antennas, where we were monitoring the temperature of the 4 resistors. And in this case, you can see the whole resistors burning up all the way to 160 degrees. We reached this roughly in 3 seconds at deployment, just to ensure deployment is successful. But of course, we couldn't really do these tests for the whole duration of the project because the bus was not complete. So some of these tests have actually been done using dummies. You can see here this nice wheel, which has a weight of approximately 300 grams. This wheel, basically hooked up to the burn wire, gives almost the same tension on the burn resistor, and this allowed us to have very repeatable tests. We also started doing some testing on our Helmholtz gauge. This is located in our clean room in Delft, where the satellite could be experiencing magnetic field as if we are on Earth, orbiting around the Earth, sorry. This gauge is also used to kind of counteract the external magnetic fields, such that the magnetic field in the center of this table is cleaner. What we want to have is a second satellite that students will use for their development on the ground, so they can fine-tune their algorithms. At that point, we will upload the code and make sure that everything is tested in space in the exact same conditions as it was on the ground. Well, let's go to the integration. I told you quite a bit about our testing, but integration. What did we do? Well, that's the core topic of this presentation, but I really wanted to show you one thing before going on, and it's the amount of hardware that actually was involved in integration. You can see here on the left side, these are all the boards we built. Okay, not all of them were inside the satellite, because we built always 5 boards. Every system was built 5 times and in a batch. This allowed us to get a production process to be quite repeatable, and also to not be too worried in case one of the boards is malfunctioning. Some of the connectors we used, as you can see here in this picture, are quite high density with small pitch, and these caused some issues in terms of short circuits or other problems. But again, this was not very critical, as only 1 or 2 boards were affected. But because of the final moments in the integration, we could basically decide not to test one of the boards and just leave it aside and focus on the 2 or 3 that were perfectly functional. So here you see all the subsystems with their flight spares being ready to be brought into the clean room. In the center, you see a picture of our clean room when we started integration, where you also start to see all the dummy panels, all the actual flight panels, spacers that were used, and all other components, thread lock. So there's quite a lot of hardware that in the end ended up in the satellite. You can see here on the top right corner, basically the 2 metal plates that build up our structure. And you can see below a picture from our partner Airbus in the Netherlands, which glued the solar cells on the panels. And actually, these are regular solar panels that they built, in this case, the Orion solar panels. So, next. Well, integration was fairly traditional in the sense that it's very much deriving from the CubeSat experience that we had. So the satellite internally is a stack of boards. And as you can see here and here, all the different boards have been stacked using stack-through connectors and spacers. Well, the solution is used by almost everybody, and we had calibrated spacers for the different combinations of boards. This is reasonably easy as a solution, but has the downside that you really need to have a lot of different spacers, as you can see in these boxes. So we basically have the complete series of all the possible heights in steps of 1 millimeter, such that we could fine-tune the integration. You can see here as well, in this corner, the satellite being built a bit more, with more boards popping up onto the stack. We are also ready at this stage to insert the laser reflector holder that you can see here, that will be fitted onto the stack, and where these wire coming from the breakout board will fit into the hole in the middle. Now, further in the integration process, you can see us assembling the attitude control system onto the stack. Actually, this was a first try. because in the end, at the last moment, we decided to swap it because in the end, one of the downsides of these spacers is that you might build up a bit of tolerance after stacking several spacers on top of each other. Electrically, tolerances are not really a big issue because the connector has a quite long, let's say, stroke, or such that it doesn't really need to be pushed all the way to the end. But of course, this metal bracket in the middle holding the laser reflectors has to be correctly aligned with the solar panels on the side. So the buildup of tolerances is sometimes a downside of this integration system. Well, in the end, it fitted. You can see a tired colleague. You can see 𝗖𝗁𝗁 now after about 4 hours of integration. And yeah, it was a long day. And this was the day before we did the vibration test. It was quite long because basically the satellite had to be integrated for doing most of the testing. But then, of course, you don't want to do all these testings in clean room because it's going to cost you more time, which basically meant we had to dismantle all the spacecraft, clean all the boards, and exactly what you've seen in a picture before where all the boards were on the table, clean everything, bring in clean room, and then integrate. So, and then after that, we went for flight preparation, gluing all the different screws, because one day later we had the vibration test. Well, we mentioned tests. These are the tests that we performed in the last couple of days of the satellite integration, which we started with a vibration test, thanks to a company in the Netherlands, to 𝗖𝘀. We were allowed to go during the COVID period, which was very complex to organize. And we managed to have a complete 3-axis vibration test, after which we had, again, electrical testing. Then we went into bakeout to be sure that all our systems were not still containing volatiles that could damage other spacecraft in the launch. Basic testing was also done after the bakeout. And to conclude, we also had the opportunity to test our radio directly with the ground station. The ground station is not located directly on our building, but it's located in another building in our campus, which is about 2 kilometers away. But in the end, thanks to the directivity of the antennas on the ground station and the power of our radio, we basically were able to receive from our building. And another nice test, you might not see much about it, but of course we wanted to see if our laser reflectors were okay. So we had to turn off the lights and check. And as you can see here, the reflection of the laser reflectors before we shipped the spacecraft. One important thing I want to mention, if somebody else will go into such a project, you need to keep an eye on your quality approach. This is key because, as you've seen in the previous slides, we had a lot of boards. We integrated 8 or 9 different boards, of which 5 of them was built every time. So we're talking about roughly 50 different boards flying around in the lab, all of them being prepared for flight. Some of them having issues, actually, as you can see at the bottom. One of the boards had a very last moment issue that we never really noticed during the previous steps of integration, basically because one of the stack of connectors had a certain resistance. And this, once everything was integrated on the flight model, was actually limiting the current reaching the burn resistors on the flight model, also limiting the temperature. What was actually realized was the fact that one of the layers of the PCB was actually not properly designed, or basically the width of traces was not enough. For 3 resistors, this was not a problem, but actually for one of them, this was a problem. So in the end, of course, at the last moment, we had to arrange a solution adding extra wires. What is really important if you aim at building more projects is to keep an eye on all these issues. That's why we relied on mostly software solutions. Like you can see, you can clearly recognize GitHub. Well, basically, most of our production issues have been tracked on GitHub. We also tracked all the development stages, basically creating issues or features to be added in our GitHub repositories. And in the end, we also looked at more automation, basically ways to keep track of all the issues across multiple repositories. As you can see here, all the issues have been tracked in dedicated projects such that we could see if something was ready or not. Basically, checking what is still left and what has already been completed. This was actually quite a lot of work, and I really think you should consider it if you're going for such a project. Well, I already started to spoil a little bit the lessons learned for the project, but definitely building spare boards is something that really helped us a lot. In case one board had malfunctioning, we didn't really have to spend time debugging it. We basically had the opportunity to simply switch. We have now a stash of boards which is, well, still needs to be checked, and we will use them for our engineering model on the ground. But we didn't really have to waste time in case of problems, and this cut our integration time a lot. Tracking issues is fundamental. Don't forget about this, because sometimes issues are repeating on different systems, and if you don't have a proper tracking, that's going to cost you a lot of extra time. So GitHub in that sense helped us a lot. We gained quite a lot of practical experience with 3D printed parts. All our 3D printed systems were done using ULTEM 9085, which is a material that has good mechanical properties, and it's also very robust when it comes to vacuum. So also outgassing level during bakeout were very minimal. But 3D printed parts are not always ready for, let's say, prime time in terms of production. You see a lot of times parts of the material which are not properly cleaned up, or parts which are protruding. So that will cost also quite some extra time to prepare the components to be integrated on a spacecraft. Of course, I'm going to say it 3 times, but I probably should have said it 25 times. Review and testing is key. You really need to keep an eye on that, because, again, you'll find problems for sure, and catching them as early as possible will cost you lower time, much less time. In our case, a lot of the issues have been tracked early in the project phases, so we could accommodate for new revisions of the systems. But actually, some issues, as you've seen in the previous slides, were caught all the way at the end. And that's actually, it's really a pity, and it costed us a lot of time to fix it. So again, I'm going to stress again, review and testing is fundamental. Quality control was also very key to us. What we saw is that after 4 revisions of most boards, we were basically able, in every production run, to get all the 5 boards we were producing to be flight worthy, all of them. This gave us a lot of possibilities to try new things. Well, we want to try a new solution for a problem that we encountered. We're not going to do it on the flight model. We have plenty of spare parts to do. So this was something that helped us, again, keep the development time quick. Last but not least, make sure students are having fun. Well, we have used a lot of students. They have been involved in the project. Unfortunately, not all the way to the end, because due to the COVID situation, the campus was closed for students, and only staff members could be present in the lab. Nevertheless, you can see the satellite here in one of the last pictures we took. Basically, after this picture, the only thing we have done was flight preparation, which basically meant refurbishing the burn wires that you can see would have been fitted at the bottom, and put the satellite in a box. Well, here we are. This is the end for now, we hope, where in the end, the satellite is ready for shipment, and it's actually now all the way in UK, ready for integration tomorrow. Now, this is the team that finished the spacecraft. We reached the end of this presentation, and you can see on the right side, Delfi-PQ inside his nice little box, hopefully getting closer to his siblings in space, Delfi-C3 and Delfi Next. So with this, I am done with this presentation. And yeah, if you have questions, please go ahead.